In sheet 4 of Conic sections, we're presented with the problem here now. Excuse the marks that seem to be coming through from the back of the page, but P is a point on a parabola, PT is a tangent to the curve, and DD is the directrix. So P is a point on the curve, PT is a tangent, DD is the directrix. Locate the focus, so they're giving us a way to go here. First thing we need to do is find the focus and then draw a portion of the curve. That's no problem. Center of curvature for a point 50 mm from the directrix. No problem, we'll be able to get onto that and there'll be no issue with that. The issue here is actually getting started. Now, you know, maybe not easy to figure out what this is. It's going to be a parabola, it's probably going to look something like that. There's going to be an axis here someplace at 90 degrees to the directrix. Don't fall into the trap of assuming that that is on the axis. Okay, I'd like to start off by just do what we know. We know that for a parabola, point to the directrix, and I should have actually started off up here saying that for a parabola the eccentricity is 1, so the point to focus over point to directrix ratio is 1/1 equal. So to apply that here, this one, I know that distance from the point to the directrix is going to be the very same as the distance from the point directrix, same as point focus. So the focal point is down there someplace along this curve. That's the first thing. We don't know where yet though. The next thing is a rule of tangents. If we can find the focal point, and if we did not have a tangent, well, if we had the focal point here, for example, and we were told find the tangent to the curve at point P, well, we'd join it, the focal to P, we'd join to the second focal point at infinity, so that ends up being a line parallel to the axis, and we'd bisect our angle, which leads on to this. If that's already bisected, I need to double it. So just once more, if I had the focal point and I did not have the full tangent and I had a point P, so I have the focal and I have point P, I would join the focal to point P, I would join to the second focal point at infinity, and I would bisect this main angle here, and it gives me a tangent. So if I can double the given angle here, I get my focal point. Now, I think I'd be expecting to see people trying to double angles by measuring them with the protractor and adding on the same. So if that was measured and it came in at 29 degrees and adding on another 29, not a very nice way to go, not very well constructed. We don't know if maybe there's a decimal in your degrees that you can't really see correctly on the protractor. Look, there's two ways. You could put a normal in at any point along the bisect line. You could put a normal in here and run that same normal out this side and scribe that distance on your compass and just flick it across to here. That will double the angle for you. But we can also do this. We can just take, I should take it from the center. We can take the length. I'm actually doing the same thing without the need of drawing an extra normal. I can take that distance and I can just scribe it out. So I've doubled the angle there by basically I'm creating the same segment of a circle. So by taking the distance here and scribing it out, I'm just mirroring the object across. That gives me a focal point right there. If I have a focal, I've already set this question up with my directrix being perfectly vertical. If the directrix is vertical, the axis is going to be horizontal. I'm going to add in my little relation right there, that directrix to axis is 90 degrees. There's my focal point. Moving on from there, locate the focus. That's done, and draw a portion of the curve. No problem. We'll get on to that now. I'm going to find, first of all, I'll find my vertex by just bisecting the distance between the focal and the directrix. And the reason I know I can do that is in the parabola, as I've said already, the ratio of a point on the curve to the focus, point on the curve to directrix, must be equal So this distance from here to here is equal to this distance from here to here. So here's the vertex. I'm going to just take some, plot out some ordinates here now. And let's go 15, 30, 45 and 60 for my ordinates. I'm going to fall really close to point P, or on point P there. That's okay. So 15, 30, 45 and 60, I'll call them number 1, 2, 3 and 4. And I'm also going to just draw the latus rectum there through the focal point as well. And now the distance from the directrix to the point has to be the same as from the focal to the point. From the directrix to the point is the same as from the focal. It falls on P to the point. And where am I now? I'm on my lattice now, so from the directrix to the focal point, from the point to the focal. So, and just the theory behind that is that the distance now from the focal point down to this point is the very same as the directrix to this point. That's the theory here. Now, if we hand in that curve, there we go. So that's the part A of the question answered. Locate the focus and draw a portion of the curve. Locate the center of curvature for a point 50 mil from the directrix. Now, I've seen this being applied incorrectly a few times. So locate the center of curvature for a point. I mean, just finding the point. Okay, finding the point here is really important. First of all, if they said located for the center of curvature for a point 50 mil from the focus, well, I set my compass. I set my compass to 50. I put it on the focus and I scribe it up to hit a point. And that point is 50 mil from the focus. But if it says 50 mil from the directrix, I can't use my compass, because I think the mistake that might be made here is someone will go right there and say, well, that's a point 50 from the directrix. But it's not, because it's much closer to the directrix here. So if it's from the directrix, we need a line parallel to the directrix. So locate the central curvature for a point 50 mil from the directrix. First thing I'm going to do is measure 50 mil from the directrix, and I'll draw a line parallel to the directrix. And it gives me two options. It gives me a point below, it gives me a point above. So use any one you want. It really doesn't matter. Use whichever one you'd like to use. I'm going to work with the top one here, right there. So drop this in with a colour just so that it stands out a little bit, and I'll go with some blue here. That is a point right now that is 50 mil away from the directrix, straight across. So I'll just call that point A, right there. Locate the centre of curvature for a point 50 mil. There we are, point A. First of all, we need a normal. Now, normal is constructed quite similar, I suppose, to a tangent. So join A to the focus, join A to the second focus at infinity, but also just bring it back in. Okay. Bisect the internal angle. And you get a normal. Now, anyone that knows, is familiar with their center of curvatures, I'm going to draw the normal and bring it on down. Now, next job is where the normal hits the axis, I'm going to run off at 90 degrees onto the focal line. So I'll extend through my focal line now as well. So where the normal hits the axis, I'll set up my sliding set squares now here. And where the normal hits the axis, so there's the normal angle, and where it hits the axis, I'll run out at 90 degrees. That gives me a point where it hits the focal line. And then I'll just repeat that task going back the other direction. So that's the best way to go with this, would be this way I suppose, where I take the angle of that focal line, I'm going to just move it just a little bit and then slide it down. Just goes into the title block there, so I'm going off at 90 degrees here again, and that gives me just under the P right there. That is the center of curvature for the point A. So just to recap that, I found point A by going out 50 mm and drawing a line parallel to the directrix. I had two options. I could have used this one below, in which case the center of curvature would be up here someplace. I decided to use the top one. I joined it to my first focal. I joined it to my second focal at infinity, and I just extended it back in this way, and I bisected the internal angle to get a normal. On the normal, hitting the axis, I ran off at 90 degrees to hit the focal line. At that point of intersection, I went off at 90 degrees again to hit the normal. So it's from the normal at 90 degrees to the focal line, at 90 degrees back to the normal. And we get our center of curvature down here. Hope this video helps. More upcoming for questions 4, 5 and 6.